So last time we met, we were talking about how different the periodic table from 1949 is from the one that we currently use today. And we were thinking about the fact that scientists have been innovating and iterating for a long time. And part of our training as scientists is to make sure that we do the practice so that we can feel comfortable innovating and iterating ourselves. So let's take a moment and think about this. Which is the orbital diagram? Which is the electron configuration? So if you have done your reading for chapter 6, which I highly encourage, you'll note that there are multiple ways or models that we use to represent information about electrons. For example, what we see here on the left, this is a great example of an orbital diagram. It shows the relative height or relative energy levels of the orbitals. It also shows the number of electrons occupying each orbital. If we look at what's in the box down here, right, this is a great example of an electron configuration that represents the number, right, total. So we can actually add up the superscripts that are shown here. So 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 2 is 20, plus 4. So we have 24. And if we're looking at our periodic table, we look for the atomic number 24, and this tells us that it's chromium. But we also have other ways that we can represent electrons. So for example, we can represent the relative electron density of electrons using orbitals. So these pseudo balloon looking like pictures show us where we're most likely to find electrons in space. And we also sometimes represent electrons using Lewis diagrams, which we'll be able to talk about in subsequent chapters. So there's multiple ways that we can represent information having to do with electrons and their relative energies. We're going to practice drawing orbital diagrams. So on your whiteboard or in your notes, or if you would like, start with your whiteboard and then transfer to your notes. We're going to talk about how we write the orbital diagram for hydrogen. So you're going to notice that you're going to draw these square boxes. These boxes each represent an orbital. So in this case, the 1s orbital. The box above it represents the 2s orbital. And the 3 boxes slightly above the 2s orbital represent the 2p orbital. In this case, hydrogen only has 1 electron, so we're going to fill the box with 1 arrow pointed up. If we think about the electron configuration and we look at our periodic table, it's the top row. So hydrogen gets the number 1, and then because it's an s, right, this represents the sphere orbital, and we have 1 electron, which is the other number that goes here. And if we're thinking about what that actually looks like if we were to draw out a representation of our atom, we have our nucleus with our proton and our neutron, and then we have our single electron orbiting that nucleus. So notice, because we have 1 electron and 1 proton, our single electron is close to the nucleus and it's strongly attracted. So let's think about another example. What about helium? So helium in this case has 2 electrons and 2 protons. So again, we're going to draw our orbital boxes and label them as 1s and 2s and 2p. And if we were to draw out our electron configuration, that would be a 1s2. That's our long configuration. And then if we just use square brackets, that would represent helium as the short configuration. And we'll see how to do that short configuration and why it matters for atoms that have a larger number of electrons shortly. So helium has a higher ionization energy than hydrogen because it has 2 protons attracting the electrons instead of just 1 in the case of hydrogen. So in this case, the energy that it takes to remove electrons is higher in helium than it is in hydrogen. Okay, it's your turn. We're going to draw the orbital diagram for lithium. So we have our box for 1s and our box for 2s and our box for 2p. Where do the electrons go? You're going to want to put one electron here pointing up, another electron here pointing down, and then our third electron is going to go into the 2s box. So our electron configuration is 1s2, 2s1. That's our long configuration. Our short configuration is to use the representation for our noble gas, in this case helium, with a square bracket, which is what's represented by 1s2. And then just the numbers 2s1. So this is our short electron configuration. We use helium as the placeholder, right, for 1s2. So in this case, we have 3 electrons and 3 protons. Lithium's outer electron, or valence electron, is in the second energy level. It's farther away from the nucleus. And so that's going to have an implication then on its ionization energy. And it's going to mean that that valence electron, right, is easier to pull off. So for example, we could form a lithium cation by removing that electron. Okay, it's your turn. You're going to draw the orbital diagram for carbon and its electron configuration. So 4 electrons, 4 protons. Let's see what you can do. Go ahead and press pause if you need more time. But let's check out our work. So we have our first box for 1s, our second box for 2s, and our third set of 3 boxes for 2p. And because carbon has 6 electrons and 6 protons, I'm going to fill each box singly and then pair, fill, and then pair. And then I'm going to fill singly my 2p orbitals. Notice, here's my electron configuration for carbon. I'm going to represent that with our square brackets for helium, 2s2, 2p6. This is the short configuration. This is the long configuration. And if I'm wondering, right, what that looks like in terms of my atoms, so here's my nucleus with its 6 protons. The first shell that has the first 2 electrons that are closest, tightest, those are our core electrons that are close to our nucleus. And then our 4 valence electrons are the outermost electrons. These are the electrons that surround the nucleus. If we think about an orbital diagram then for fluorine, go ahead and take a moment and draw your orbital diagram. This is the electron configuration and orbital diagram for fluorine. It has 9 electrons and 9 protons. That means that 2 electrons are going to be closest to the nucleus. They're going to be our core electrons, and then we're going to have 7 valence electrons. I want you to think for a moment. We typically see fluorine becoming a fluoride anion, where it's gained an electron. What would the orbital diagram of that ion look like? What would the electron configuration of that ion be? Take a moment on your whiteboard or in your notes, draw the orbital diagram and the electron configuration for the fluoride or F- anion. If you need more time, go ahead and press pause, but we're going to move on and check our work. So notice, right, all I've done is add 1 more electron because that's what fluoride as the anion gain. What I really want you to see here is this 1s2, 2s2, 2p6 is the same electron configuration as neon. That's critical because if I think about this, right, I can represent F- as just the square bracket and E. So now that you're confident with writing electron configurations, go ahead and figure out the electron configuration for bromine. That's element 35. You can write the shorter noble gas notation for the electron configuration as well. And if you don't have a periodic table, here's one that is provided for your use as a reference. Again, press pause if you need more time. But here we go. Bromine, you'll note, is in the fourth row. So it's going to be 1s2, 2s2, 1s2, 2s2. So 1s, there's the 2, 2s, 2, 2p, 6, 3s2 is sodium and magnesium, 3p6 is argon, and then 4s2 is potassium and calcium, 3d10 is what we see here, and then 4p5 takes us up to bromine. If we think about our short configuration, we just go to the previous noble gas, which in this case is argon, and then we fill our 3d10, our 4s2, and our 4p5. So that's a great example of practice with electron configurations. I've got some additional worksheets to help you make sense of that and to practice drawing out your orbital diagrams. Thanks again. Talk with you soon.